Alright, so now let's discuss on Fourier series. So basically what we're going to do is, when we do Fourier series, so we are going to be given a periodic function, and what we're going to do with the periodic function is that we are going to transform the function. So what are you going to transform the function into? So instead of like in terms of the periodic function, so we are going to change that into a series of sine and cosine. Of sines and cosines. So that is what we do when we do Fourier series. Okay, that is going to be the idea of Fourier series. And how do we do the transformation? So it's going to be using this particular formula right here. So let me highlight the formula and put this in a box. So this is going to be the formula, and in the appendix section you will be able to find the similar formula. So the function is given by, so instead of the periodic function that we have seen before, which is, for example, is going to be in terms of this form right here. One is going to give you the shape, one is going to give you the period value. So you're going to change it into something like this that looks as a series of cosine and also sine. So the formula is that f of t is going to equal a half a naught plus sum of from n equal 1 to infinity of a n cos n omega t. So this over here, this is not w, so it's called as n omega, and plus sum from n equal 1 to infinity of bn sine of n omega t. So I have three coefficients over here that is going to be very important, known as a naught, an, and also bn. So this coefficients, let me put over here. So a naught, an, and bn. So they are known as the Fourier coefficients. So are known as Fourier coefficients. Alright, and each of them has an individual formula. For example, if you were to start with a naught, so this is going to be the formula for a naught. It is given by 2 over capital T. So remember, you have come across the symbol capital T before. It is going to be the value of the period, and integral from d to d plus t. So this value of d and d plus t will be from the question itself of the function f of t dt. So when you integrate, substitute the lower and upper limit, so you will get what is going to be the function an. And please bear in mind, the an is always going to be a constant. So the rest of them, a naught is going to be constant. The rest of them, an and bn, they are going to be in terms of functions, but a naught is always going to be a constant. It's always going to be a value. It could be a value of 1, it could be a value of 2, it could be a value of 3. But the main point is that it's going to be a value, a number. And for the case of an, so this is going to be the formula for an. Okay, so this is going to be the formula for an. I have 2 over t integral from d to d plus t. So f of t cos of n omega t dt. Right, so here, so the difference between the formulas that here I only have f of t. So now I have f of t being multiplied by cos of n omega t. And of course, omega has a specific formula. So this is going to be the formula for omega. So omega is given by a formula of 2 pi over t. So you know what t already. So t, capital T is going to be the value of the period. Right, so we'll get that from the question itself. And the last one is going to be bn. So bn is going to be 2 over capital T, the integral from d to d plus t of the function. So now our function is going to be f of t sine of n omega t dt. So that is a slight difference between them. So this is f of t multiplied by cos, but for b of bn, it's going to be f of t multiplied by sine. Okay, and again, you don't have to memorize any of this. So if you have a look at the appendix, so let's revisit the appendix. So it's going to be here. No, this is notes on Laplace inverse. So this is my appendix. So everything is going to be here. So this is Fourier series. Everything is going to be in here. The formula for omega. So what is going to be f of t? The formula for each of the Fourier coefficients, a naught, an, and bn. So you have to memorize nothing. Everything is simply going to be given. Okay, so that is going to be in terms of the general formula of Fourier series. And before I start with my first example, so I want to revise a little bit. I know that I have explained this to you before. I think it was in 4.2, but I start my lecture on 4.2 for a reason, because I think it's easier for you to understand. And we have seen this before. So I mentioned to you that when we have the case of an even function, like when you have an even function, automatically if you don't draw, you have to know right away. So the fact that they are going to be side by side, I have no idea how it's going to look like. Probably it's going to look something like that. Okay, but we have to know the fact that the function is always going to be symmetrical about the y-axis. It's going to be a mirror image, this side and this side, and they are going to be symmetric on both sides. So that is why, so when we have an even function, you don't have to think further. So what you can do is you can use the property. All right, so instead of like integrating from negative pi to pi, so negative pi to pi, so the range is going to be from negative pi to pi. We know that there's going to be 0 in between, and so the area is going to be symmetrical. So when we have two symmetric areas, the left and on the right hand side, so what we can do is, instead of we integrate the whole area, so we can integrate only half of the area. I'm going to integrate only this area, and I'm going to multiply that by 2. So this is what I'm going to apply over here. So t, we have seen this before, t to the power of 1. So this is going to be an odd function. Sine is an odd function as well. And when you multiply odd and odd, it's going to be even. I explained this to you in 4.2. So if you don't have this in your mind at this moment, go back and revisit 4.2. So what I can do is, instead of like integrating the whole thing, remember you have to substitute the lower and upper limit, and you don't want that. You want your calculation to be as simple as possible. So what we can do is we are going to integrate only half of the area. So therefore, I'm going to integrate only from 0 until pi. And of course, when I wanted to find the whole area, I have to multiply by 2. But my function here is going to remain. So I'm going to multiply t of sine to t dt. But now, the limit has changed. It's going to be from 0 until pi. What is the purpose of doing so? Because of course, substituting 0 is going to be much easier than having to substitute negative pi. So that is the major reason. Okay, and if you substitute negative value into your sine or cosine later, you have to use another property. Okay, and you want to try to avoid that. You want to try to minimize the mistakes. So that is why when you come across an even function like this, so you can change the limit and integrate only half of the area, like what I did here. And for odd function, so it's going to be an even better. It's going to be even better, because the thing is that when you draw an odd function, so we have no idea exactly how t cos of pi t looks like, but what we have in mind is that we know that one function is going to be, for example, if it looks like this at the top, one function is going to be right at the bottom, and they're going to be symmetric. If this is negative pi, on this side this is going to be pi. And remember, so if your area is above the horizontal axis, it's going to be positive, and if it's below, it's going to be negative. So that is why, so this area, which are the same, they're going to cancel each other. And when you come across something like this, an odd function is going to become odd, because this is an odd function, this is even, and when you multiply odd and even, it's going to be odd. And because they are symmetric, one at the top, one at the bottom, when you add them up together, they're going to cancel each other. So therefore, this is going to equal 0. It is always the case when you integrate an odd function, so that is symmetric because they have the same region over here on the left and on the right, automatically the outcome is going to be 0. You don't have to do any further calculation, so just put that it is going to equal 0. That's it. Okay, so that will be the introduction part. Okay, so now let's have a look at this function right here. So I have a periodic function, f of t. I'm going to start with my first example on how to do the calculation. So which is defined by f of t is going to equal -1 from negative pi to 0, and 1 from 0 until pi. And if you remember, I did explain to you before in the previous topic, the fact that the first function is going to tell you about the shape, and the second function is going to tell you about the value of the period, so which is denoted by capital T. And for this case, what is our value of period? So that is going to equal 2 pi. And from this shape over here, what's the reason of identifying the shape? Because you want to know whether your function is going to be odd or even or neither. So what is the purpose of knowing them? Because of this function, because of this, so that you will know when you integrate, either you're going to use this property or this property. Okay, so it will happen tomorrow for your integration. Alright, so now for A, so first we're going to sketch the graph in order to identify the shape. And so the purpose is identify shape, and after we have identified the shape, we're going to start with the calculation, and we're going to find the Fourier series. Okay, now let's start sketching. First of all, have a look at the interval. So here it has been given in the question. The interval is going to be from negative pi until 3 pi. Of course, every single time. So the interval